First and foremost, good morning. We welcome. Today will be one of the final days when it comes to actually working on the syllabus. If there is anything you don't understand, if there is anything you have problems with, just ask and I'll be able to help you as best as I can. So today's lesson, whilst I'm using Volhard, I'm also using this book, Mechanisms in Organic Chemistry by Peter Sykes. Okay, you don't need the book. So far from it. Don't feel that because I'm using a book, you have to use the same book. Anzi, I'm using this book because it's useful. Anything that I'm giving you, I will be writing on the board. I will also then prepare some sort of document so that you have all the notes in one place. But I will say, for anyone who wants to continue in organic chemistry, this book, a guidebook to mechanisms in organic chemistry by Peter Sykes, it's a must. Okay, it has most of the mechanisms that you will be using even without going into masters or PhDs in organic chemistry. But if anyone is doing organic chemistry next year, I think it's a useful book. Secondly, I would like to speak a little bit about the format of the exam and the sheet I've given you last week. So let's actually share the screen. Have you all by now seen the sheet given? So these questions were all questions taken from either past papers, because I have some access to past papers prior to 2005, 2006, when boards used to give this subject, okay? I think, whilst I have access to those papers, I will not be sharing them with you for two reasons. Primarily, the syllabus has changed, and it used to be a combination of photochemistry and what we're doing in organic 3. So if I give you the paper, there will be quite a few material that you will not be able to answer. Having said that, I would like that you are capable of answering the questions I put in the practice sheet. I will be updating this list. I will be updating these questions in the coming days. So I have a few more papers. I have a few more questions not coming from the University of Malta, and I will be updating. Access to VLE, it's still not open. Okay, so it's not, if you can't access it, it's not from your side, it's from the university. For some reason, it still hasn't been opened. So if you need to upload practicals, if you need to do anything, at worst, just send them via email. At worst, but they normally upload it to VLE for the safekeeping, and if you need them again in the future, you will be able to find them. Just like I would be able to find my past practicals in different chapters. But again, for now, don't worry about it. At some point, we will be able to sort it out. I'm still hoping they will sort it out soon, because now it's becoming a bit of a problem. Now, any one of you or anyone has tried to answer these questions, I know that some students have sent me some questions via email or Facebook. Facebook for me is a good enough tool to send me questions. It's as long as you feel comfortable sending questions on Facebook, I will answer. I know that some students might not be too keen sending questions on Facebook to a lecturer, okay? But I don't mind. I prepared the Facebook group so you can ask questions there, but I also prepared the Facebook group so you can see my personal Facebook account, and you can contact me there with any queries. Don't worry about it. I understand that in reality, you need to be able to feel comfortable with your work, and you need to be able to feel comfortable actually asking queries, asking questions. That's how you learn. Okay, let's see if there's anyone in the waiting list, in the waiting room. So, have you tried to work the questions? Has anyone tried to work the questions yet? Before I start thinking about the exam? Nothing. Yes, I understand, but I'm just asking, just to be. So, the questions that you have up till now, there was one question you couldn't probably work. In reality, I gave it to you anyway, because with what we've done till now, you could have done something a little bit different. But the questions you've done, you can actually do them all. From today onwards, you should be able to actually answer all questions. I think the syllabus will be finished off today. Then, as I was saying before, I would like to do a little bit of research synthesis. I think research synthesis is very, very, very important. Okay. And I think it's something that is very, very crucial with respect to moving on with organic chemistry. I would like to do a little bit more synthesis, and eventually I would like to do a lot more when it comes to answering mechanistic questions, okay? Because up till now, I believe that your mechanistic questions, we haven't really covered too many yet, okay? But that's something that we can do later on. Issa, the exam. I'm a big fan. I'm not sure if Professor Borg is still doing it, but I am a big, big fan of something that Professor Borg used to do in the past. He might still be doing it right now, where you have questions similar to question 1 here, where I give you the reagents and you give me the product. They will be 1 or 2 marks questions, normally 2 marks, okay? And you just need to give the product. No mechanisms, no nothing, you just write the product, okay? Now, the recommendation by Professor Zinagra for the exam is this. It will be a 2-hour, 45-minute exam, and I will prepare a mock exam. The mock exam will be so that you have an idea of what's going to happen. I don't see the use or the need of actually doing a lot of past papers. I will be giving you, because I know that some of you actually feel more comfortable by getting some past papers. I will be giving you some past papers, okay? The past papers you should be able to answer fully. So if there is anything from the past papers you can't answer, contact me and we'll see why. But I will be giving you a mock paper because the format will be different. There will not be 2 sections like previous years, and like the sample paper I gave you last time, but there will be 3 sections. The sections will be, I think, either 60, 20, 20, or 40, 30, 30. And the aim of the question, in my opinion, is going to be very, very simple. Okay? Section A is going to be simple questions that you have to answer irrespective of, no, without any choice. Section B and Section C, you will have some choices, but instead of giving you the choice of actually going into choosing 2 questions from 3 or 2 questions from 4, you'll have 1 from 2, and you'll have to answer any type of question. So 1 will be mechanisms and 1 will be synthesis. Okay? I think that a lot of times, a lot of students misinterpret those questions as, I can skip from studying this part of the chapter. I don't want to be in that position. I want you to study everything, and once you study everything, then I will be able to pick and match what I want you to know. But from the perspective of the student, you should be able to have studied everything. Now, I don't want to scare you with the exam. The exam is not going to be too hard. Okay? At the end of the day, the exam will be an open book. Just because it's an open book doesn't mean you'll have a lot of time to actually look at the books and at the notes. So make sure you're comfortable. Don't be that student who actually has gotten his exam, okay, and instead of actually going on and studying beforehand, you see the question, you see the mechanism, you try and go and find it. You will not succeed in doing that, okay? It's a tough exam. I can't have an exam where everyone gets over 80. Remember, it has to be moderated. I would like for all of you to do well. I will be giving you all the support you need to do well, but then again, there will be a few questions that are a bit tough. But there will be nothing that we haven't either spoken about it in class, it's not in your notes, or it's not in the book. For books, I know that some students are using different books. I am using Volhard, okay? So as long as it's on Volhard, you should know it. Let me make that clear. As long as it's in Volhard and it's the chapter that we're currently doing, you should know it, okay? I will be giving you the tools to actually succeed in getting it right. So I will be explaining over and over again how to get certain things right, but it will be, in my opinion, up to you to make sure that the chapters we've covered, you know. I will not, and I'm gonna emphasize this because I know that some of you are worried about it, I will not be asking you questions that are from other exams, okay? I might reference a little bit NMR because I think spectroscopy is very important, but I will not be asking you questions directly on NMR, okay? Let me make that clear. For me, if I give you an NMR, you should be able to interpret it, okay? But I will not be asking you to interpret the NMR. I might be asking you, why are there 3 peaks only? Or why are the ratios 2:1:1? Okay? But it will be up to you to actually work and to actually understand what I'm doing. Okay? Now, the syllabus. This is the syllabus that you've got. There are a few things where we've covered everything. There are a few things where there are a few items that are missing. With regards to chemistry of aliphatic nitrogen compounds, everything has been covered apart from formation of sulfonamides, nitrization of amines, we covered them slightly, and the diazomethane, carbetane, cyclopropane, these are in effect in the notes I've given you. We haven't done them you can just read it. It's just knowing what a carbene is. For me, it's not examinable in this exam. So I will be covering probably later on, just so I have covered all the syllabus. But for me, this is not, I will not be using it in my exams. Okay? Carbenes are very important. Carbenes, if any of you have actually done inorganic for transition metals, they are very useful there. But again, I don't see the point. I don't see the use of doing them in organic chemistry at this point, because we're not going to be studying carbenes at any stage at this level. Chemistry for aromatic compounds. Again, everything has been done. I would like to go a little bit more detail on sulfonic acids. Okay. And apart from that, I will be doing the Benzine mechanism. The Benzine mechanism is something that is useful, that's important, but unfortunately, it's very difficult to do it in a lab. Okay, so I knew what I was doing when I skipped certain parts in the chapter, but now is the time to make sure that we've covered all the syllabus. Phenols, we've done all the reactions as far as I'm concerned. We have not probably done the bakelite formation, but again, the bakelite formation, it's a polymerization. And together with what we covered earlier on, I would probably be saying that I would want you to do this on your own. Simply, I can explain it, but I would like you to simply do this on your own for one particular reason. At the end of the day, because we've covered the basics of this mechanism, this is a polymerization. I would like you to be in a position where you can actually go and read and understand it. If you don't, ask me and I will be able to help you. Okay? A means you've got a mechanism here, Gomberg. I'm not entirely sure for what you're referring. We've covered everything that is in. We've covered everything that is found in Volhard. Okay? Again, with me using Volhard as your primary book, then I'm not going to be too focused on something that is not on Volhard. Okay? So you can not worry about it. Polycyclic aromatic hydrocarbons we haven't done, we're going to be doing them today. Okay? And we're going to be using the same format as what we were using beforehand. And heterocyclic compounds, I would like to do the synthesis of pyridine, and the others, they are then exactly the same as what we've done before. If you want pyrimidine, metazole, indole, quinoline, and isoquinoline, I will show you the structures, but you don't need to go into a lot of details of how they react and everything. Okay? I hope we're clear with regards to what we're doing and what we're not doing. Then I would like to spend a little bit of time on other areas of organic chemistry with respect to these topics. So retosynthesis for me is going to be very important because I will be dealing with it with respect to this topic. Okay? Rather than with respect to alkanes or alkenes. Are we clear with regards to the syllabus? Now, today I'm going to be using my board. And if you have any queries, please, I will see if I will send it on the Facebook page later on today. No? So Let me connect my tablet with my computer so that you can be seeing the board. One second. Because I dropped my tablet. Apologies. So, first things first, I would like to start with the benzine mechanism or nucleophilic aromatic substitution. Now, you are probably not used to having a nucleophilic aromatic substitution because in reality, you have always done the electrophilic one. But that is not entirely true. Whilst you may think you've always done the aromatic one, the electrophilic substitution, that is not always true. Because you have one reaction at A level where you added NaOH. So, in this reaction, there are no electrophiles. Oh, sorry. There are no electrophiles. Okay? Now you should be able to see the board on its own. Beforehand, you had to click on it. Now, because there's no electrophile, the conditions are a lot tougher. And the conditions are a lot tougher mainly because you actually need to break the Cl bonds first. And the route this takes goes via this reactant over here. And that is the benzine. So, as we can assume, the benzine is highly reactive. So, in this particular reaction, the actual rate determining step is not, and let me make this clear, it is not the step to go from the benzine to the phenol. It is actually to form the benzine. Now, why is it tough to form the benzine? Because you are breaking a carbon-halogen bond and you are also breaking aromaticity. So, benzine is not aromatic when compared to the chlorobenzene. Okay? Benzine is not aromatic because benzine has 2, 4, 6, 8 electrons. Issa, you can put the argument forward that it's got only 6 electrons that are planar, so it should still be aromatic, and I might consider you to be right. But you have 2 electrons, 2 pi electrons that are going to be very reactive. Okay? And that's where it reacts. So what happens? In this particular reaction, you need to remember that you have a very strong base. And if you have a very strong base, that can actually do that kind of mechanism. Okay, so the OH minus attacks the proton, which then attacks and eliminates the chlorine or the chloride ion to form the benzene. Now, as an intermediate here, you will have that kind of intermediate. And this is highly, highly reactive. Okay? So the intermediate for the benzene is the anion. So this is not really a concerted process. Remember, concerted process, the steps happening at the same time. There is an intermediate, but it's the OH minus attacking the proton or the hydrogen, and then the Cl is removed. You need to use strong bases. So you can either use NaOH or you can use NH2 minus. If you're going to be using NH2 minus, you can introduce the NH2 group. If you're going to be using NaOH, we'll be introducing the OH minus. What I will be telling you to be a little bit careful about here is that there are better routes to get to both the phenol and the phenylamine. So in my opinion, even though, and this is why I did the reactions first, okay? In my opinion, if I give you a synthetic route, I don't want the shortest one. I simply want the one that is most efficient. So I would normally not touch these reactions unless something extraordinary has happened. Okay? I hope I'm being very clear here. Now, these reactions can be quite high yielding actually. So with regard to yields, they can still work really, really well. But what these reactions do not have are favorable conditions. Remember, every time we're actually doing a reaction, I am considering what is happening. I am considering that I need to do this in a lab. I need to be safe. I don't want to waste too much energy. Remember, if I'm using a reaction at 30 degrees, it's better than doing a reaction at 200 degrees, let alone 200 degrees, 200 atmospheres. I hope I'm being clear here. Doesn't mean that this reaction you will not have it in your exam, but as I told you, I'm really considering that you will have the first section just full of reactions. Okay? But I would like you to actually be in a position where you know which reactions to choose if you're going to be doing these in an actual practical or in an actual experiment. Okay? So with regards to nucleophilic aromatic substitution, that's all I have to say. It's an interesting reaction, it's an easy reaction, it's a reaction that you've been probably doing since you were in your A-levels, okay? But it's also a reaction that you might have forgotten about, okay? And the mechanism, you have never actually studied it. Now, next thing that I wanted to speak about is sulfonation. So sulfonation we've done it as a reaction where you have the sulfonate. What do you mean addition of water to the benzene?
Sorry, hydroxyl group konti qed ngħid mill-benzine.
Okay, it's OH minus, ta?
Eżatt. Imma ħabba li għandek triple bond għalhekk jiena tinsaqsi.
Because that's explained. Give me a second.
All right.
Give me 1 second. Let me see if I can find the mechanism for that as well. Because as far as I'm concerned, you don't have it, that part. So, that's your benzene, right? Now, let's say I have OH minus. So if it's a let's understand the process. It's a nucleophilic, aromatic substitution, right? At this point, it will be a nucleophilic addition. So at this point, you've already eliminated the Cl. So you just need to add the OH minus. So I will add the OH minus to one of the 2 points. It doesn't really matter, okay? And you have to flow the electrons. So if electrons are going on one carbon, the triple bond has to break and it will go to the carbon adjacent to it. And this will produce this compound right here. Now, an anion on benzene, because this is what it is now, okay, is going to be very, very basic. Okay? It's going to be very, very basic. So if you have water, then it will simply take a proton from the water to produce the OH minus. Okay? So in reality, you will be regenerating the OH minus used. Again, this bit of the mechanism here, it's just continuation to how we've prepared our benzene. The benzene, you need to destroy it, right? And you're going to be destroying it the same way you've made it. You create it by removing Cl minus. So as soon as you add DOH minus, it's the reverse reaction. It's the reverse reaction with different mechanisms, with different reagents. Okay? So in the Cl minus, you're now putting in DOH minus. Okay, Steve?
Thank you, yes.
So sulfonation is this reaction. Now, this reaction is something that we normally use simply to prepare phenols. Up till now, we have not really used sulfonation for anything else. Okay? We just use it to prepare phenols, and that's it. But this reaction is reversible. This reaction is reversible. Okay? And because this reaction is reversible, you can use it as a protecting group. Who can tell me what a protecting group is? What is a protecting group?
It's one where functionality can be restored after the reaction being done.
So it's a group that you introduce so that, let's say, your alcohol will not react. Okay? So the alcohol is protected. But for it to be a protecting group, it has to be a reversible reaction. So functionality is not just restored, it's safeguarded. ħafna drabi protecting groups are, for example, with ketones forming hemiesters. Okay? So you have a ketone and you don't want the ketone to react with a nucleophile. You react it with alcohols, okay, with diol to form a hemiacetal, and the hemiacetal protects the functionality. Because it can then be removed, because it's a reversible reaction, and once it's a reversible reaction, then you would be able to actually get your ketone back. So here you can put the SO3H to introduce something else. Okay? So you can put the SO3H, so you go to carbon number 2, outside carbon number 3, and from there you might want to put on another carbon, so on and so forth. But sulfonation, it's pretty much very useful to introduce a group called sulfonamide. Qatt smajtu bih sulfonamides? A sulfonamide, read it aloud, a sulfonamide is this group. So you're replacing one of the OH groups with nitrogen. Now, sulfonamides are very, very important when it comes to drugs. In fact, a friend of mine was working on these to try and see if we could do them using radicals. Okay? The current synthesis is to actually go through the acid fluoride, so we simply add PCl5 or SOCl2 and then you can add the amine. Okay? And this reaction, as I said before, could be a bit of a problem because when you have a reaction where you are adding such a reactive reagent, let's say it's your 6th or 7th step synthesis, you have to be careful that this does not interact with anything else. Okay? There is a lot of research ongoing on sulfonamides, mainly because they've just now started to realize how important these are, especially in antimicrobials, antibiotics. Okay? But there are very few ways how to actually make them. Okay, so if anyone wants to be successful and to probably win the Nobel Prize, if you find a very good and easy way how to make sulfonamides, this would be highly appreciated. Now, when it comes to your syllabus, with regard to sulfonamides, you just need to know how to make them. Okay? And you need to know that the reactions are reversible. Now, there's also something called the Kingsburg Test. The Kingsburg Test is a test to distinguish between primary, secondary, and tertiary amines. Okay? Mainly because primary and secondary forms very stable. Okay? Sulfonamides, tertiary, do not. Okay? But again, I'm not going to be asking you about this. To be honest, if I were to ask you about something like this, you can simply go on Wikipedia, you can simply go on Google, look it up, and you'll find it. There's no knowledge here. And the difference is this. A secondary amine and the tertiary amine. Which one of these will be soluble in water?
Tertiary amine.
The tertiary one. Okay? So the tertiary is a salt. Therefore, you can distinguish between primary and secondary and tertiary. Now, in all fairness, yes, this would be a good way how to distinguish between primary and secondary, or tertiary. But in my opinion, there are better tools at our disposal, even at the university in Malta, to do this. Because you can use NMRs, you can check the integrals, okay? So the integrals here would be 6 is to 2, 2, and 1. Or if you want to play it safe, it's 6 protons on NH3 on CH3 compared to 5 aromatic, sorry. Okay, now why did I actually say 5 aromatics rather than separate them as 2, 2, and 1? Because as you might have realized, the aromatic peaks are most often than not hidden, and they are together. So you won't see separate peaks, okay? Especially probably in a compound like this, where the functionality will not shift to the left or to the right that much. So you will end up having the aromatic protons very close and similar to each other, okay? And in the tertiary case, you'll see 9 compared to 5. Again, you can use mass spec. Mass spec is also quite nice here because mass spec will give you the mass, and if you have the mass, then you can actually get it relatively easily. One thing you can't do with mass spec or NMR is to separate them. So if your final aim is to separate the mixture, so you have a mixture of secondary or tertiary amines and you want to separate them, then you can't do that using mass spec or NMR. Then you need to use something like this method. This method is called the Kingsburg method, okay? But I've personally never seen anyone using it. So I was working with amines. I've never actually used this method because there are other tools, okay? Even possibly using something like column chromatography would be better. Now, so chemistry of aliphatic nitrogen compounds and chemistry of aromatic compounds, they are done. So I would like to speak a little bit about polycyclic aromatic hydrocarbons. First and foremost, I would like to speak about naphthalene and its reactivity. Okay, and then I would like to speak a little bit about how to make naphthalene. Once we can make naphthalene, then we can go on and make other structures, such as anthracene, okay, and phenanthrene, I believe you have. Yes, anthracene and phenanthrene. Anthracene and phenanthrene, they have the same number of carbons and hydrogens, they are just bonded differently. So, naphthalene is pretty much two benzene rings fused together. Okay? So naphthalene is this group. And naphthalene can react on two positions. On position number 1 or position number 2. 1 or 2. And pretty much these are the only two positions it's got available. And I want to make it clear, even though there are 10 carbons, there are only two positions available because we can say that this is also 1, also 1, and also 1. Okay? Because they are all equivalent. Before we start adding anything, they are all equivalent. I hope I'm making myself clear. Remember, this is a resonance structure, okay? Naphthalene doesn't really exist. 3 bonds and 2 bonds. Naphthalene is a fully aromatic compound. Okay? And naphthalene is 2 fused benzene rings. So this is fully aromatic. I hope I'm making myself clear here. Now, so what happens and how do we choose which position we undertake? Whether it's position number 1 or position number 2. Okay? So the first thing to do is that you have to draw the resonance forms. If addition happens on position number 1, and if addition happens on position number 2. I would like you to draw resonance forms for both of them. Okay? It's very possible to draw the resonance forms for both of these compounds. So please feel free to do this. Electrophile. So anytime you see E in chemistry, it's an electrophile. Now, being able to draw resonance forms of any structure without saying it's important, okay? Because let's put it this way. At this point, you are second years or third years. For those who are in second years, you are actually doing something that, in my opinion, should be done in third years. In third year, okay? You have to realize that being able to draw resonance forms is crucial because resonance forms give you a lot of information. Now, reactivity, in fact, here, C1 will be more reactive. And both structures actually have 5 resonance forms. So I would like to draw them, in fact. Okay? Both structures have 5 resonance forms. So why is it that one of them is more stable than the other? Actually, no, let's draw them. So let's draw them, okay? And see how things go. Did you all attempt to draw these? Now, expect, and I mean this, expect resonance forms in your exams. So when we actually start speaking about reactivities, I will be expecting you, and I can't be more direct than how I'm being now. I will be expecting you to know how to draw resonance forms and how to elucidate information from those drawn resonance forms. So, the first step that could happen, you could have that moving. You could have this moving. You could have that moving. And you could have the last one moving as well. And remember, when these are moving, okay, they can go back. What I don't want to see is someone drawing this line here. You cannot go from here to there, so we don't draw a full circle. But they can revert back simply by going all the way back. Okay? And you have 5 resonance forms. You also have 5 resonance forms for this position to attack. Okay? Now let's see. You can see on the board, right? So let's try and fit this to attack as well here. Is there anyone who has problems drawing the resonance forms? You don't need to write on chat. Just communicate with me so I can give you a few exercises on these. Because resonance forms are going to be able to help you a lot understand quite a few parts, a few chunks of this topic. So those are the 10 resonance forms, 5 and 5, okay? And this is the reason why, in fact, naphthalene reacts in position number 1. And naphthalene reacts in position number 1 because, why do you think it reacts in position number 1? Because it's a bit more stable. So, ħafna drabi, we work in a system where we look at the number of resonance forms. But in this particular case, the number of resonance forms are the same. It's 5 and 5. But here, you only have one structure where you have a benzene ring which is stable. Okay? And remember, naphthalene, you're breaking aromaticity. But the benzene ring, or at least one of the rings, could still be stable. So here you have one resonance form where you have some stability coming from the benzene ring. In position C1, you have two resonance forms where there is a bit more stability on the benzene ring. And that makes a bit of a difference. It makes a difference. Why? It makes a difference because this would therefore be more stable. If it's more stable, it will exist for longer, and therefore it will react more. It will be a bit more energetically favorable to react. If you were to increase the temperature, the reactivities start getting closer and closer. At 180 degrees Celsius, for example, the reactivities are pretty much identical, if not favoring the C2 position. Okay? So I think you've done this in thermodynamics. You have the thermodynamic favorable product and the kinetic product. They don't have to be the same. Okay? So here, T1 is what will take place. Why? Because you have two resonance forms that still have some stability from the benzene ring. Okay? Same mode, you can also go and work with anthracene and phenanthrene. Okay? But I will not be giving you any of these to work. But at least if you go to page 747 on Volhard, not now, take a look, because you are asked to actually know that C9 or C10 are the ones where that will be attacked. And what I can ask you for the exam is to draw the resonance forms of an attack on C9 or C10. So I would very much like it if you actually go and draw this out. Again, I'm not telling you, I will be asking you to draw all the resonance forms for all the possible attacks on phenanthrene. That's impossible. Okay? There are so many carbons that can be attacked. And in phenanthrene, they are not all the same, not like naphthalene, where you have 1 and 2, irrespective of where you start. Then it will be impossible for you in an exam to actually draw them all. But to be able to compare, okay, to compare resonance forms for 2 particular points, that's important. Now, with that out of the way, because sometimes I think, I don't want you to think that the exam is going to be easy and straightforward. It won't be. But then again, I don't want you to be afraid of the exam, because it's nothing to be afraid of. Okay? But realize, resonance forms are important. I know that some of you might actually be afraid of resonance forms. Don't be. There's honestly no reason to be afraid of these. Now, how do you make these? It's one of you, I don't think I've seen him today, but one of you have asked me a question. Okay? And because we haven't done these, I told him an answer that suited what we had done up to that point. So, And in fact, this is actually one of the questions that you have in your practice sheet. So, this is called the Horrid Method. And the Horrid Method actually uses a couple of important principles. The first and most important principle is that aromatic structures are more stable. So if you get a system, a cyclic system, that can end up being aromatic, is going to be favored. Okay? So that is probably the most important concept here. So what you need is benzene, and you need an anhydrate. And for simplicity, let's assume that R dash are the same. Okay? That's for simplicity's sake. Let's assume that R dash are the same. And actually, preferably, let's use this one, solid anhydrate. If we were to use AlCl3, this reaction will happen. Pretty much, this is acylation, okay? So for acylation, normally you use the acid chloride, okay? But the anhydrides are nearly as reactive. Therefore, there is no reason for this reaction not to take place. If you wanted to make a bit more reactive, you can have an R group on the other side. Okay? So the R group will direct it on one position only. But again, there is no reason to either use the R group, and you can also use the acid chloride. But this is, of course, a bit less reactive, therefore it's a bit more usable. Now, once you get to this position, what you do is you use zinc amalgam. So zinc, mercury, and HCl concentrated. Okay, this is something that we've done and we've used at A level, and this is for hydrogenation of ketones. And at this point, you are halfway there. You are halfway there because at this point, you have managed to actually get one carbon-carbon bond, and you removed an oxygen. Now, the next step might seem that it is a bit difficult, because the next step, we are eliminating water and forming a new bond onto the ring. And we are simply using H2SO4 and heat. But because this is an intermolecular reaction, because this is an intermolecular reaction, this would actually be favored. Okay? So normally have a tendency that these reactions cannot take place. But normally they cannot take place because they are intramolecular. So you would have different molecules colliding, and therefore the collisions would not be favorable. But because this is an intermolecular reaction, the reaction would actually be favorable. And if we repeat the process with zinc amalgam, then you can actually get a hydrocarbon. Now this hydrocarbon is not aromatic, or this hydrocarbon is not naphthalene, because this ring here is the benzene ring, so it is aromatic. But apart from that, it's not fully aromatic. Okay? Again, if we want to incorporate the R, we have to incorporate it everywhere. To get to naphthalene, just add selenium and heat. To add to naphthalene, just add selenium and heat. Now, the interesting thing about this reaction is that you don't have to use it to produce naphthalene only. You can produce any aromatic ring. And I mean it, any aromatic ring. So you can use this to make anthracene from naphthalene. Okay? You can literally make any ring that you want. Okay? Because then, instead of using benzene as your starting material, you can use naphthalene. Okay? It doesn't matter. You can use anything that you want. Now, do you know why these compounds are quite bad to our health? These compounds are polyaromatic hydrocarbons. And these are highly carcinogenic. Okay? I'm not sure if you've ever heard Professor Sinagra speak, but Professor Sinagra does a lot of research with regards to these pollutants in the air. Apologies, yes, it is. Steve was right, it's right, okay? With zinc amalgam, you use HCl concentrated. Now, so these are highly carcinogenic. First and foremost, when they burn, they do not burn to completion. So they leave a lot of particles. Secondly, even them themselves, if you inhale them, you can actually do quite a lot of damage with them as impurities in your body. Okay? You can do quite a lot of damage because they can interact with enzymes, they can interact with your DNA. It's not something you would normally probably want. Now, the last thing that I would like to do today, before I speak again about what I want you to do with regards to the practice problems, is this. I would like to share with you the Hunch synthesis. The Hunch synthesis is a synthesis that we use to make pyridine. This is the Horrid method. It's not in your book, by the way. That's why I actually drew it up here. And the next one, the Han synthesis, is in the book, but I think it could do with a little bit more detail. That's why I'm gonna do it here as well without the book. So certain reactions that I think the book doesn't have, Walhart doesn't have in a lot of detail, I'm actually trying to do them extra just to be on the safe side that you have good understandings. So in the Hunt method, okay, we use a few compounds. We use an aldehyde, we use diketones, and we use ammonia. Now, as far as you're concerned for the exam, okay, if you can go from the aldehydes and ketones and ammonia and get to the final product, you are halfway there, okay? From the final product, you should be able to actually get to the pyridine using nitric acid and KOH and CaO. So this is first you hydrolyze, no, sorry, first you oxidize, then you decarboxylate. But I would like you also to be able to do the steps. Now, here, a lot of you might not be that comfortable with these reactions over here. Okay? But even if you don't know the mechanism, and I do not expect you to know the mechanisms, okay, I would like you to be in a position where you know what the intermediates are. And the intermediates are actually quite important, okay? So first and foremost, something similar to the aldol reaction here, okay? You can get a carbon, double bond carbon on the position here, okay? So in reality, this is the most, you can all see the screen, right? The screen that I'm sharing. Okay, so you can first deprotonate this position, okay? So you have a negative charge. That negative charge can then attack the aldehyde, which then can lose water to form the double bond, similar to the aldol reaction. Now, when I say similar to the aldol reaction, doesn't mean that the aldol reaction has to be exactly like this, okay? But it's got similarities. Once you note that you have two diketones, okay? So this is the first diketone reacting. The second equivalent reacts in a different fashion. The second equivalent reacts with the ketone to form an iminium ion, okay? Or an enamine in this case. Now, don't go to the detail of how this enamine is formed. You don't have to. But remember, nitrogen or nitrogen compounds can attack the carbonyls, similar to what you used to have at A level, okay? And similar to what you've done even in this chapter, I believe. Or in this module, not chapter. but you'll end up having an enamine. Again, this is a bit more stable because you can have some delocalization. These two intermediates can now react. Okay, so these two intermediates can react. And this is a concerted process. Realize it's starting from the lone pair on the nitrogen, pushing all the way through. Okay, so this is what I want you to be able to understand from now on. Nitrogen pushing in, you go to the carbon, pushing in all the way to the oxygen. Okay, so it's a 4-step concerted process to get to the structure over here. Because it's not clear, the structure has an O minus, and an NH, or an N plus. Okay, you've got an O minus and an N plus. If you add ammonia, you can remove the extra proton. And you end up in a position where you have a negative charge on the oxygen only, which is a lot better than having two charges. Now, there are some resonance forms because of that negative charge, because the negative charge can be stabilized going through the other oxygen. And this is why it's important to have the group at the end. Okay, this is why you need to have a double bond O at the end as well. You need to have an ester, not an aldehyde, simply because the reaction will continue reacting otherwise. So the ester group will stop the reaction. You still have the oxygen, but it's not reactive enough as a carbonide to react with anything else. Once you have tautomerization, okay, do you remember what tautomerization is? Tautomerization is the keto-enol. So this is, you can consider this as an enol here, okay? It's the keto-enol isomerism. So you can form the ketone. And once you form the ketone, then you can have reaction between, you have a negative charge over here, forming a double bond, the nitrogen interacting with the oxygen and forming an alcohol. So now you formed the basis of your pyridine. Okay, then you can remove water to get a second double bond. Then you add ammonia and move the charges around. Okay, and now you have something like a quinone. These are very easily oxidizable. Okay, and you end up being in this position over here. Now, let me make this clear. This mechanism is not in your syllabus. Okay, you have the synthesis. The mechanism is not in your syllabus unless I give it to you in the exam. Okay, so the mechanism is not in your syllabus unless I give it to you to discuss. Now, the Hunch method is important because you can form pyridines with a number of functional groups. And this is probably the easiest way how to introduce functional groups to pyridine. Because pyridine is a lot less reactive, if you remember, than benzene. Okay? Pyridine is a lot less reactive than benzene. Now, having said that, this is a method how to introduce functionality. Okay? Because the R groups can be any R group that you want. But realize, if you want to introduce functionality using the R groups, then you have to take note and this is quite crucial at this point, you have to take note that your reaction might interfere with the functional groups. So the functional group should not have carbonyls, for example. The functional group should not have bases. But a simple functional group like a chlorine or bromine should be fine. Okay? Something to substitute later on. Now, with this in mind, I think that, yes, let me show you these structures. So, pyrimidines are groups where you have, pyrimidines are groups where you have N double bond O N. Okay? So it's not an amide as such. But I'll prepare a few notes and I'll show these next week. I'll show them all. So let's change the camera again and stop sharing. Well, yes. So today, for me, okay, everything that I want to examine you on, everything that I want to make sure that you know, I think that by this point you do. I'm not gonna tell you that you will not learn anything new in the next 4 weeks. But as far as I'm concerned, for the next 4 weeks, I am more focused on actually teaching new techniques and new skills in how to answer these questions, and how to write mechanisms, and how to understand mechanisms, than I am in actually covering new topics. Okay? So what I will be doing is that I will be giving questions and answering questions. If you don't have any queries from beforehand, that's fine. I will be working a few problems myself. Okay? I'll send you the problems beforehand and I'll work them on the board. But I would like you to start practicing. You have the luxury, and I'm gonna say this without any shame. You have the luxury that this year you actually have the chance of doing your exams at home. And that's the truth. The truth is that these exams are gonna be easier. Don't waste it. At the same time, the syllabus is done. That's why the first Monday of the holidays I told you, I asked you to actually have a lesson, so that the syllabus would be done as soon as possible. If you look at past papers, there should be nothing that you can't answer, but there might be a few questions with regards to stereochemistry, okay, that we might want to delve a little bit deeper. It's not that in this particular topic you have stereochemistry, far from it, but at least if it actually comes to the point where you have to study stereochemistry, okay, where you have to be reminded about a little bit about stereochemistry, we can do that as well. Same with NMRs, okay? If you need a little bit of revision on how to read an NMR, we'll do it as well, because from now on, I would like to start toughening it up. So we've done the knowledge, we've done the theory, now you need to actually start doing the practice, okay? And for me, the practice is probably going to be, well, with regards to you, will be the hardest thing, because I'm gonna be asking quite a bit out of you, I think. Okay, but then again, remember, as long as you have your Volhard with you at home and you have the chemistry portal website during the exam, then you don't have a problem. You should be able to actually be able to answer everything. Okay, for today, we can stop here. Thank you for your time. Thank you for your attention. If you need anything, please remember, don't hesitate to contact me. Some of you have spoken to me, okay? Either through emails or through Facebook. I don't mind which one you use, okay? Just feel free to do so. But at the end of the day, I will leave it up to you. Thank you for your attention. If you need anything,